So let's continue this morning session by the last talk in this morning session by Professor Rinat Kashaev, and his title is a simple model for 4D TQT.
Thank you very much. Thank you, Jon. I'm going to talk about a really simple model in 4 dimensions. Model for TQT, which is a state sum model. And let me just start right away defining it. So we start by some triangulated format. Related oriented format. So triangulation means that we have a set of I-dimensional simplices. And we will assume also that all vertices are linearly ordered. So delta 0 of S is linearly ordered. For example, enumerate from 1 to up to the number. And then we can define a sign map which sits on the set of 4-dimensional simplices, which is equal epsilon of p equal 1 if the orientation coming from the linear order, from the order vertex order, coincides with that with the orientation of the manifold itself. Okay. And we fix a root of unity. A root of unity. And now we define first the notion of a state of X is a map from 3-dimensional simplices of X into integers modulo n. And so I will use a terminology for simplex. I found in the internet that it is called pentacoron. Analog of tetrahedron 1-dimensional. Okay, so pentachoral wave function. That's the principal ingredient of the model. So we take a pentachoron and the wave function of it associated with a given state. So the state I use just exactly as it is used in the context of knot invariance. So it is given by 1 over square root of n, omega to the power epsilon of p, x0, x4, delta of x0 plus x2 comma x0 plus x2 comma x1, delta of x2 plus x4, x3. So these are delta Kronecker deltas. So xi, by definition, is a state on the facet I of T. And we define m omega of x as a sum of over states, product over all pentacora of the weight functions, and divide by n to the power number of vertices. Theorem: m omega of x is equal to m of y if x is equivalent to y. So in the sense that they are triangulations of one and the same for manifold. So this is the main result. And remarks. So this easily extends to a coordinative. So if you have a three manifold with boundary triangulated in the way that the boundary is also triangulated, then you fix the state variables on the boundary and do the same thing, but sum up only over interior state variables. The result will be a number indexed, a set of numbers indexed by the boundary state variables, which gives a vector in a vector space, which is evident to guess what is a vector space. And in this way, we get a TQ of T, because on gluing, we have to, when we glue along a common tetrahedron, then we multiply the corresponding matrix elements and sum up over the state variable sitting in this tetrahedron.
Just a question about the vector space. So the vector space, I think, is just C to the n times delta 3.
Exactly.
So the particular depends on the number of tetrahedra you have used for the 3 manifolds.
But this is a TQ of T where the morphism of a cylinder of a three manifold is not identity in that vector space. It's a projector.
So you could take the image of that projector,
Right.
and that would be a topological.
That would be true TQ of T in the usual sense.
Sorry, Nat. So for S3 cross S1, do you know the value?
Yes.
Ah,
So
maybe that will
this was the
explain to us the
first
dimension.
remark.
Also, are you going to tell us why this weight function? I mean, for instance, the two delta functions.
Yeah, I will
explain
tell.
how-
I will tell
Yeah, these variables. It
if
looks
the
very
time
mysterious.
allows.
But no quantum dichotomy.
Nothing.
What's this?
That's the most complicated part of that.
Yeah, it's amazing. I mean, that exactly.
Okay, so I think that's the one of the
I don't see my second remark. Okay, so m tilde of omega of x will be n to the power 3/2 Euler characteristic of x times m omega of x. So we will consider also this combination. This is the definition. Now examples. Let me say a few examples. What was the question? What was the main?
S3 cross S1.
Okay. So S3 cross S1. 1. Any other?
The force sphere maybe comes now.
1.
CP2.
Yes, CP2.
But this is independent of omega.
Right. But I normalized. I normalized. So the M omega is different.
You could always do that. It's just
So this is not different. This Euler characteristic is 0. But here Euler characteristic is 2. Which means that the M omega of S4 will N power minus 3. CP2 a little later, let's say
Okay, S2 cross S1 cross S1.
S2 plus S1 plus S1. It's a 3 plus minus 1 power n half.
so far it still doesn't depend on omega.
No.
Only on
So it
n.
is 1 if n is odd, and 2 is
I
n.
can also do that calculation, but it doesn't depend on omega, only on n.
Yes.
So this is every
Yes.
no,
So
it has to be.
Good, I love it. Am I allowed to ask?
K3.
oh no, too complicated. No, it's too. I don't know simply. It's, I need to calculate. Same. See. Now CP2. This is the principal example, and the answer is this. That makes me little optimistic about the non-triviality of the invariant.
Wait, how about S1 4 times, just a torus?
Yeah. So this I know. This I know.
So that's actually important.
But
Is it?
I think so, right?
This is unpublished result.
So the original invariant gets complex conjugated when you change the
Yes. Yeah. I didn't say
It's
that's.
unnatural.
That's what was my second remark actually. Okay, M omega of x star is M omega of x. So it distinguishes CP2 bar.
M omega of x bar, but that's also the same presumably as m omega bar of x. Of course, well, obviously, yeah.
Yes.
Obviously,
Yes. Thank you. That's good remark.
No, I'm sorry. I guess example now 2 and example 4 are very important.
2 is this one.
Yeah. And
1, 2, 3, 4. This one.
yeah.
Okay. Why?
I'm sorry. Maybe. Sorry. 4 and 5. No.
It depends on the numbering.
What I want. Sorry. The key thing to observe here is Euler characteristic and signature.
Oh, I see. Yes. You explained me another time. Yeah. So these two examples have both zero Euler characteristic because they have S1 component, and the signature here is trivially 0 because the H2 is trivial. Here H2 is not trivial, but signature is still 0. And but the invariants are different. So It's not the invariant depending on only Euler characteristic and signature, at least.
But they're distinguished by their homology. So you have
Yes,
the
yes,
same
they are
formula.
distinguished by homology, but I'm thinking about Crane-Yetter invariant of 20 years ago, which was the first example of TQFT in 4D, and it happened to be independently of homology, or simply connectedness as a function of two classical invariants, Euler characteristic and signature. So this is not the case here.
So,
But you are right, still it can be just homotopical invariant in principle.
You don't have an example where it's not distinguished by homology, but it is distinguished.
No, it's I spent a lot of energy and time on calculating this too. Because you need triangulation.
But can you say anything about connected sum? Or is that-
No, unfortunately no.
no?
One has to understand how connected sum, two triangulations are related in a connected sum.
Can't you,
I don't know.
can't you just put one triangle in common and then remove it? One pentachora?
It's non-multiplicative under connected sum?
Might be. I just didn't ask myself.
Well, no, there's a formula, of course. You just take out the one simplex for one simplex for
But that's
the
what I
other.
thought.
Yes.
And you put it back in both, and you just.
Yeah, but you see,
Yeah, but
so
how the sum will be
exactly.
behave? That's you cannot predict.
your sum, yeah.
It's not obvious.
Not obvious.
But this isn't obvious either. Then we can still ask.
But yeah, maybe.
But if you take
It is a TQT, right? So you can compute the.
Yeah, you have to
whole
know
thing.
when you remove one tetrahedron, you have to know what is the dimension of this cobordism. When you remove a tetrahedron, pentagon, then it is a manifold with boundary. So the result, the partition function of this guy will be a vector in a vector space, and you have to know what is the dimension of the vector space this vector sits in.
But there is S3 cross S1.
Why is
The dimension of S3 cross S1.
why? If you have a complicated manifold like this, remove one pentacoron, why it should be related to S3 plus S1?
Yeah. So have you tried to compute a 3 simplex cross I, the operator for that? Because the operator for that is exactly going to tell you what the space
oh, that's
is.
good. It's just amazing.
No, I don't remember that I tried this. Okay, so I don't know the answer.
And
for
also you
connected.
said it's complicated because the triangulation, but here you've given a formula for each of these 6 manifolds for all n. But if you
Yeah.
take some slightly more complicated manifold like S,
No,
some small n, can you do
difficult.
it?
No, the difficulty is in triangulation.
Okay.
Difficulty is not the calculation because, as you see,
No, but you can certainly triangulate a connected sum.
you have.
Wait, but you can triangulate a connected sum, you just agree.
Yeah, no, but
So
the
if you
point,
take just a connected sum of two S2 cross S2s, that's a famous manifold. And
Yeah,
then just
maybe,
some
yeah,
computers,
maybe,
some
yeah.
small omega-
Yes,
but you
that's.
see the main thing is the 3 simplex cross I, and the question whether that endomorphism has rank 1, because if it's rank 1 it must be multiplicative of some form, but if it has higher rank it may not be multiplicative. It's a TQFT, you see, so you can compute from the pieces
Yeah,
by the 2 boundary
right,
vectors
right.
and then the inner product. So if that's higher dimensional, it will not
Yeah,
necessarily be a perfect
That's a good
product.
point. That's and I didn't do this. So
First thing, just numerical.
this is relatively easy actually
Yeah,
to
I
calculate
thought
this.
so, yeah, it's a formula.
There might be, there might be programs like Regina that
Regina for 3 dimensions. Yeah,
No,
Regina very
four
useful.
ones.
Very useful to single out a true for manifold. Because if you glue arbitrarily pentachora, a discrete set of, then a priori it will not be a 3 manifold. It will be you have to check that the links of edges and the vertices. I think it is enough to check the link of all vertices.
Yeah.
And Regina is very useful in that.
But this is also an invariant for these pseudo full manifolds.
Yeah, it is. It is. Yeah.
You can still get an invariant.
Yeah, but I don't have. I know one example of a 2-knot, which is whose complement is triangulated into pentachora, and the invariant is 1. So we need at least another example of.
And
but do not.
you have to have manifold for this theorem. So, for instance, if the links of vertices are homology 3 spheres, could
Yeah. You can just any triangle. Actually, that's a third remark maybe. So one can use a delta complex. Generalized notion of triangulations. So just the cellular complexes where all cells are simplices, and all gluings respect the linear order.
So you don't need that it's a PL manifold.
No,
For the
it's
theorem,
yeah. Of
this
course, it
theorem.
works in the case of triangulations. You can refine any delta complex to a true triangulation, but in practice, of course, it's better to work with delta complexes because in that case you will have fewer cells, the number of cells.
No, I mean I meant actual triangulations, but where, for instance, the vertex link is no longer 3 sphere, so then it won't be a manifold, but it's still triangulated.
Yes,
And then it works. Yeah,
works,
okay.
works. Okay, so that's the description of the examples, and so in the remaining, if I have remaining time, I can outline how the proof goes. Okay, so the proof consists of checking two things. First thing is the invariance on the partner moves. So these are analogs of Regenmaster moves for knot diagrams. So there are finitely many local changes of the triangulation which are enough to relate any two triangulations of a given measure. But besides of this, one has to check that nothing depends on the linear order of the vertices. Okay, so let me put it this way: tensor chord C, which boils down to independence of the choice of the linear order on the vertices. Okay, for the first thing, we have three types of Platnar moves. So KL type KL with K plus L equals 6. Why 6? Because one has to recall what is a Platnar move. You take delta 5 simplex, and then you take its boundary, which is composed of 6 pentachora, composed of 6 pentachora.
And what is the Greek name for 5 simplex?
Chorus means space, so this means
So you need another one with hyperspace.
five sectored.
So you need a hexa hyperspace. No, we want the Greek word after pentachora. The next.
Hexachord.
No, because space is 3-dimensional. Now we have to go one up. You want 6 higher dimensional things.
How do you say 6 in Greek?
Hexa.
So,
The next.
Yeah.
no.
Okay. This one.
Yeah.
It's number vertices.
So the Platnar moves corresponds to splitting of the boundary pentachora into two non-empty subsets, complementary non-empty subsets. So this is why they have to sum up to 6, and then you can split 6 into how many ways? So 1, 5, 2, 4, and 3, 3. So we have 3 types of Platnar moves. And the most fundamental one is the symmetric one of the type 3, and it can be written in algebraic form. We have a pentagon. Vector 4. Okay, pentagon. And then we draw it. We can draw it like this. D0 of P, D2 of P, D4 of P, D1 of P, D3 of P. I separated even facets and odd facets differently because they get opposite induced orientations. Like in a boundary map, in the simplicial homology, it is given by alternating sum of face maps, and the sign is given by the parity of a face map. So we sum up the even facets and subtract the odd facets. And here we distinguish them by putting even facets upwards from the box corresponding to pentagon, and odd facets downwards. And then the identity. Okay, so I can draw, yeah. And then we take 0, 1, 2, 3, 4, 5. So the power set of this finite set corresponds to the standard combinatorial 5 simplex. 5 simplex. And then okay, let me call it U, then di of U, which is U sub I, will correspond to U minus vertex I. So we threw away one element in this set, then we will get a pentacoron which corresponds to I's facet of U. And then the picture is the following. So we have U0, U2, U4, and then we have 3 legs entering like this, 3 legs entering like this. Yes. U4. So this should be equal to 3, 4, 5, 6. U5. One, two, three. U3. U1. So you have correspondence. We have 3 legs, open legs in the left hand side, and they should be identified correspondingly. So this leg in the left hand side of the equality corresponds to the lower leg here, second, and so on, and upstairs the same. So this crossing is needed just to make sure that this open end corresponds to this open end, and so on. So this is the identity. And in TQFT, this is supposed to be a linear map from TQFT. This becomes some map Q from V tensor V to triple tensor product of 3v's. And so you just write the composition of linear maps according to this diagram. So this is a 3-3 move. And so it is just a very easy exercise just to substitute this Q x0, x2, x4, x1, x3. Okay, this thing should be thought as a matrix element of this Q map. And then you just compose, and the summation of this those interior edges, just very easy check. And then similarly you treat the other moves, but this time you have to, for example, to get 4-2 move, you pick up one of those odd U's and put to the left hand side and connect accordingly along the corresponding tetrahedra, which is shared by those even U's and this odd U. And for the last one, you transfer 2 odd U's in the one side and contract accordingly. So again, if you remember in the partition function, I divide by n to the power number of vertices, which means that the 1-5 relation will be true up to factor n here, and the two sides of this partner move are distinguished by the fact that in one side, where you have 5 pentachora, one vertex is interior. So the move corresponds to the erasing one vertex, and this is accompanied by multiplicative factor n, which is taken into account by this normalization. And finally, so this is the first part, and the second part is treated in the following way. So we just have there is this two linear maps S and T, which map this n-dimensional vector space to itself, such that if we take this linear map Q, which maps from tensor square of V to tensor cube of V, then it can be written also as P tensor T tensor T bar tensor T applied to Q bar. And this relation corresponds to so remember that Q corresponds to a pentagon with linearly ordered vertices. And let us just take first two vertices and exchange their order. And this corresponds to multiplication by permutation operator of two legs. And then this is accompanied by action on so this Q, sorry, I forgot to say that Q can be written as an element of V, tensor V Jul, tensor V Jul, tensor V, right? Which means that I turn so I turn just upwards all the legs, but then I should distinguish between vector space V and dual vector space. As in matrix analysis, we always have a linear map corresponds to a vector in the tensor product of the target space and the dual of the source space. So this formula is written by interpreting Q like this. So you permute these two, and then multiply. This is inverse of it, and multiply along these three legs by those matrices, and you apply it to Q bar, which corresponds to omega inverted, which is a unit inverse of Q, not inverse, but Hermitian conjugate of Q. And so this gives you an idea. When you exchange the order of only two vertices, you change the relative orientation, the sign. So if you had Q bar, then it becomes Q. And so you see that really you can achieve this physically by acting on the boundary spaces. So this exactly reflects the invariance under the exchange of the order of two first vertices. But there are three more relations like this, which look like T tensor P tensor S minus 1 tensor S acting on Q bar. So this time, as you see, P jumped in the second position. So you exchange two other components. So you exchange now the second and third vertices, the order. And still you have a similar transformation formula, which in the partition function, so permits to make sure that the state sum doesn't change, because all these transformation matrices will cancel. And the third one, so you go similarly. So S tensor S minus 1 tensor P tensor T. We need four of them. Okay, so and one more T tensor T minus 1 tensor T tensor T. So these four relations induce the whole pentagonal group, which is simply S5, permutation group of 5 vertices. So if you wish, these are just four generating elements in the permutation group. Okay, I stop here. Thank you.
So questions?
You didn't say what T and S were, but
Yeah, I didn't say, but this doesn't matter.
you still have 10 minutes.
Huh? You want to see them?
Yes, because
Okay, yeah.
everything else you can do in any dimension, right? Except for this.
Well, you need a solution, right? You need Q, analog of higher dimension.
But you also need S and T.
For symmetry, yes, but those ST will not work in the higher dimension. It is very peculiar to 4 dimensions. Okay, so if I define phi of m to be omega m plus m over half, over 2, then T acts on em gives omega minus m. So these are dual bases, okay? This is in V. Omega is not good, right? So phi dual basis. Then if we act by T to em, then the result will be vector in so T and the S and go from V to V star. So T em goes to phi minus m times this phi of m, and S em goes to phi L phi m minus L sum over L. So this kind of transformations. Yeah, here.
This kind of reminds us of the torus. I mean, V should be the vector space of the torus in the Abelian theory.
Yeah, this the notation is intentional from conformal field theory, S and T matrices, but I don't know any reason. Because if you take just matrix element, right, T, em k, this will be delta m minus k phi of n, which is analog of diagonal matrix giving the dimensions, conformal dimensions.
Well, is this an SL2? Do they satisfy S squared and SDQ equal 1?
So there is no algebraic interpretation in terms of quantum group theory. This I don't know. But I can say you one secret. This solution comes from quantization of dihedral angles of ideal tetrahedra in 3 dimensions. Namely, the Poisson, Neumann-Zagier Poisson structure. So, in a sense, this is a quantization. So, there is a set theoretical solution obtained by just reading out arguments of 5 dilogarithms in the Rogers 5-term identity. So, remember that L of x plus L of y to L of y minus xy 1 over xy plus L of xy plus L of x minus xy 1 over xy. So this is a Rogers 5-term identity. And then you just do the following thing. You take q, put xy downwards, and put xy in the middle, x minus xy over 1 minus xy to the left, and y minus xy over 1 minus xy to the right. And then if you check the diagram which I've drawn, but using this set theoretical map, then the identity will be satisfied. But on the other hand, these are cross ratios in ideal tetrahedra. And each cross ratio can be parameterized by 2 dihedral angles, 2 real dihedral angles. You have a Neumann-Zagier Poisson bracket there, and then you just quantize this map with respect to Poisson bracket. In that case, it will be infinite dimensional solution, but you can put it into roots of unity and make it 5-dimensional. Effectively, this is how the solution comes out.
I didn't have a question, but an answer to one of the previous questions, namely my own. In your examples, it always depended only on n, not on omega.
No, CP2. CP2 was
up to sine, maybe. Up to sine. Because that omega to the x squared, it's Gaussian sum and it transforms just the right way.
No, but its phase depends on the Jacobi symbol, right?
But that's only a sign. It's a sign. So
I see.
Up to
I
sign.
see.
And I think that's a general thing. So you can, at least if you maybe squared or invariant, you could just call it an n of x. And the reason is very simple. First of all, I think there was also a typo in the formula that you erased. It was omega to the power epsilon of p times x0 plus x4.
Yeah.
You wrote x0 times x4.
It's times.
That doesn't make sense. It's additive.
No, it's bicharacter. In general, it's bicharacter. This solution can be generalized to any locally compact abelian group, and then omega to KL you replace by bicharacter. So it's additive separately with respect to both arguments. Which
you wrote the other variables additively.
No, all of the variables were in Z multiplied NZ, but
Right,
that's still a ring.
the sum is written additively.
No, but that's still a ring.
it was a sine, right? Sine and n and L. That was it. So x0
Times x4.
x4.
And you really meant that? Okay.
Yeah.
No, then my comment. So I thought you meant to multiply. them.
No. It's
Combine
just
that.
product. But in general, it's bicharacter. You have a locally xy by character, which means that it's additive with respect to separately each of the arguments. For fixed x, it is a representation of the group. And
but the part with the delta is additive. That was x.
it is additive.
So if I take a collection of xi's and I simply double, I multiply x by a constant, I multiply f by a constant, then the delta condition is the same.
Yeah.
But now I'm Galois conjugating the whole thing. but that new f will still satisfy the same conditions. I mean, you're summing only over those f's where the deltas are not zero.
Yeah.
If I double or multiply all the xi's by some constant prime to n, then I don't change those deltas.
Right.
And if that constant is c, then I'm just replacing omega by omega to the c squared.
Yes.
So therefore, since I'm summing over all x's, that means that the whole sum does not change when you replace omega by omega to the c squared. But that usually will be the whole Galois group, I think. And that's why I think the things essentially in the ground field are very nearly.
I see.
It's simply because of that remark. But I thought it was the sum, but it equally applies to the product. So there is a sort of an obvious Galois effect, because you're summing over everything. So it will be a much smaller field, maybe even almost always.
Yeah, I wonder. I still doubt about non-triviality the result, but I hope it will give something. But
It's utterly amazing.
Yeah.
Yeah, so you mentioned it works for delta complexes. What if the triangulation has only one vertex? How do you find it in the order?
with no, but the order means that in that case means that for all triangles you don't have cycles. That's the meaning of the order in that case. So no triangles with cyclically ordered edges. Yeah, that's a good question. Yeah.
Any more questions? Thank you.